Girls from the science class. I'm going to try something a little different today for our day 2 of the Trebuchet Gizmo. Um, Based on the fact that I think it's taking too long and some of you are getting stressed out about that, this is an option for you to just follow along with what I'm doing on my screen and hit the pause key whenever you need to enter your data. The first question on day 2 asks us to set the trebuchet up using these dimensions here, and we're going to be analyzing the short arm length and the changes that that has on the initial speed. So I've preset the dimensions up and put the short arm length at 1. And now I'm just going to launch and see what happens. Okay, and then go back. It's asking us to put in the initial speed. So keep an eye on the initial speed down here is 18.97. So I'm going to do 18.97. I'm going to skip the meters per second right now just because it's going to take too long to do. Now I have to set it up for 2 meters. Okay, so I go back to my reset, set this arm length, short arm length at 2, and launch the test. Okay, and it says the initial speed is 20.54. So 20.54. Now I go back and reset it and try for 3 and launch test. The initial speed is 32.18, 32.18. Okay, again, go and set it for the arm length for 4, the short arm length that is for 4, and launch. Initial speed is 40.34. Might be able to identify a pattern at this point, change that short arm length to 5. And remember, I've got to speed these up. I only get 15 minutes per video. Launch test. Okay, the 46. And the final one is at 6 meters for a short arm length. Okay, and launch the test. Thinking that should say test launch instead of launch test. And 48.41. 48.41. These are all in meters per second, so you could go back and put your labels in if you want. Meters per second. Okay, now taking a little bit of time here to set up Trebuchet 2. The counterweight is 6,000. So I'm going to reset, make my Trebuchet 6,000 for the counterweight, and 40 for the payload, 40 kilograms that is for the payload instead of 200. And my fulcrum is 9, long arm 9, sling 9, and the other things are the same. Okay, 9, a 9. But then we want to put this short arm down to 1 again because it does still want us to look at the short arm. So we are going to be testing out the short arm. Okay, so I'm going to launch. Smaller payload, much larger counterweight. The speed is 42.49. So 42.49. Okay, change the next one to 2. So reset. We're just messing around with the short arm at this point. Okay, launch. And 75.95. Big jump there. Okay, going to 3 meters. And launch. Okay, and it's at 87.55. 87.55. You could round these two. There'd be really no problem with rounding all of these numbers off. Okay, reset and go to 4. Launch. Okay, and it's 86.01. 86.01. Go to 5 meters. Launch. We get an initial speed of 78.12. Interesting. Okay, we'll take a look at this data in a minute and then reset it to short arm to 6 and launch. Okay, and I get 67.54. 67.54. Now the question down here says analyze, compare Trebuchet 1 and Trebuchet 2. On Trebuchet 1, the initial speed increased from 18.97, 20, 32, 40, 46, 48. So on Trebuchet 1, there was consistent increase in initial speed. On Trebuchet 2, there was an increase in speed and then a decrease in speed. So it went up, increased up to 3 meters and began to decrease on 4 meters, 5 meters, and 6 meters. So if you wanted to answer how do the trebuchets differ, you could say T1 had an increase in initial speed throughout the 6 tests. T2 increased initial speed for tests 1 through 3 and decreased speed 4 through 6. I think that would be just a acceptable answer for that one. Moving along to the second set of question, or the next question, question B, for Trebuchet 1, which short arm length produced the greatest initial speed? So for Trebuchet 1, which short arm length produced the greatest speed? Well, that would be this one, 48, the 6 meter one. So that answer is simply 6.0 meters. For Trebuchet 2, which short arm length produced the greatest initial speed? Go back up and look at my data for Trebuchet 2. Which arm produced the greatest speed? And that was the 3 meter arm. Okay, so I go back and type in the 3 meter arm. In general, what short arm length maximizes the initial speed when the payload is heavy compared to the counterweight? So in this one, the payload in Trebuchet 2, notice the payload is small and the counterweight is heavy. In this one, the payload is heavy, 200 kilograms. The counterweight is 4,000. So the question's asking, in general, what short arm length maximizes the initial speed when the payload is very heavy compared to the counterweight? Okay. Now, I would say that Trebuchet 2 has the biggest, when I was thinking that the question, the payload is heavy compared to the counterweight, then we're talking more about Trebuchet 1. Payload is 200 kilograms compared to the counterweight of only 4,000 kilograms. There's a very big difference between 6,000 and the payload of 40. That's a big difference. But when the payload is heavy compared to the counterweight, then it's the longest short arm that you can have maximizes the speed. So that's a tough question. That's a really tough question. I would say, in general, the longest short arm will maximize initial speed. How does the optimum short arm length change when the payload is very light compared to the counterweight? So how does the optimum short arm length change? On this one, I think, well, let's take a look at the data. But now when the payload is light compared to the counterweight, the optimum length, you can tell, that means the optimum is the best, is this one, 87.55, so it's at 3 meters. So the answer would just be that it's at 3 meters. So we would just say it is when the short arm is at 3 meters. Okay. Now moving on to this next part, activity B. Select the launch tab. Now we're going to be checking out the siege of Acre. And so we're going to go back to here and we're going to click on the launch pad and make sure that this says siege of Acre. And what we want to do is follow the directions here to breach the wall. Well, and it does help to read the story here a little bit. Basically, it's a little bit of history, and they're trying to get breaching this castle. To breach the walls of Acre, your projectile has to hit the walls with enough force. What is the distance from the Trebuchet wall to the city walls? Well, it says it right here. The range is 111 meters. The height is 15 meters. So the 111 meters. Okay, so we have to put in 111 meters. The projectile's kinetic energy depends on its mass and speed given by this equation. We learned this equation, except we used S instead of V. In this case, V is velocity, and speed and velocity are very consistent. Velocity is just speed in a given direction. Now, how much kinetic energy is required to break through? It says it right on the gizmo. The required kinetic energy is 140 kilojoules. So we put that in, 140 kilojoules. On the design, set counterweight to 4,500. Okay, so we're going to do that. So now you have to go back to the design tab and set the dimensions up as it says. So 4,500, oops, 4,500. And you need to have the payload at 160. Okay, payload at 160. And then I'm going to check these other dimensions here. Fulcrum 9, short arm 3. Fulcrum 9, short arm 3. That was our optimum initial speed. And then long arm 9, sling 5, long arm 9, sling 5. Make sure you get these dimensions right or it's not going to go well for you. And then the prong to 40, okay, which we're at. And then it says to launch the projectile. Okay, so we're going to go back to the launch pad though, and then click play to launch it this time. Okay, we are going to fall short of the castle, but the projectile went a total distance of 74.5 meters. So 74.5 meters. Okay, let me undo that. What just happened there? 74.5 meters. What was the impact? What was its impact kinetic energy? Impact kinetic energy was 101.2 kilojoules. So 101.2 kilojoules. And I did it again. Don't want to waste time here. Okay. Click reset. Use what you've learned as well as trial and error to create a trebuchet that can fling a projectile and break the city walls. So now this is where the fun comes in actually on this one. You have to just do some playing around here and see what you can do to make it finally hit the wall. And then what you're going to do is once you get to that point where you can hit the wall, you put in what all of the dimensions were. What were the dimensions that you finally figured out? And then this is where you put the screenshot in. So this part's not that difficult. I'll go through, I've only got about 2 minutes left on my video before I have to end it. So we'll see if we can quickly hit the wall. Okay, so I'm gonna click reset. Go to my design, let's see, maybe a bigger counterweight, 5,000. Let's change the prong angle to maybe 30 and the sling length to 7. I don't know, let's just try it. Okay, and then practice. Okay, I think I might have flung it over the castle. Yep, I flung it too far. Okay, so I'm going to go back to the drawing board here, and I think I'm going to put my sling length back to 5 and try that. Something happened. Okay, so that one's not going to work. So I'm going to go back to my design and maybe my sling length of 6. Okay, and let's try that. That was almost a bullseye. Bullseye. Okay, projectile hit target, but not enough energy to break through. I need more energy. Okay, so I need more energy, which means I need a bigger payload. Now this is going to take too much time. I'm at 14 minutes and 35 seconds. But you can see how you have to do some trial and error. And then what I would do is go back to design. Once I'm successful, take a picture of it with my tool, screenshot, and then put in my parameters here. Okay, hopefully this was helpful. I can do part 2 if we need it.